Okay. Good afternoon. So in the previous class we looked at the single stage operational amplifier. So our single stage operational amplifier looked like what? You had a supply rail, and then on top you had the active load. So I can draw my active load. Active load is drawn. Please draw along with me so that it's practice for you. You should be able to draw these things quickly. Okay, that was your active load. Then what was there underneath the active load? You had your differential pair. The differential pair was connected thus, and then at the bottom you had another transistor, right? And that was part of a current mirror. So you had actually some kind of a current source there. Okay, so all of you understand all the things that are there in this particular circuit, right? So could you understand this about say 3 weeks ago if I had drawn the same circuit? Now are you able to at least see the blocks? So when you get a big circuit like this, don't go and start analyzing everything from first principles. First try and identify if you can find some blocks that you understand. Once you find those blocks, you will be able to see the big picture, and then you can analyze it in a quick way. Alright, is this correct? Alright, so for this, this was our single stage op amp. Okay, what was its differential gain? Differential gain was what? GM n times RP. Okay. Now because we have only so we call these transistors as M1, M2, then this was M3, M4, M5 and M6. We did some kind of approximation to the characteristics of these transistors. I said that M1 and M2, they have a gain of GMN and their Rn was infinity. M3 and M4, they have a gain of GMP, and I said that its gain was RP. Alright, and then M5 and M6, they have a gain of what? Okay, let me call that as GM5 and GM5 slash GM6. Okay, it had an output resistance of R0. Now while calculating the differential gain, we did not take this R0 into account. While calculating the common mode gain, we took it into account. You can take everything into account and calculate everything, but I am not interested in doing that right now. Okay, common mode gain. What was the common mode gain? -2. So no, that was wrong. It was a small number, no? So it is 1 by 2 GM what? P R0. Okay, right? And what can you say about these things? This guy is high, this guy is low. Okay, it's high but not infinite. And what did you find about the R out and R in? R out was not infinity, sorry, R out was RP and your R in was infinity. Okay, now you can go back into the previous lecture and find out what were the conditions under which we found all these things out. It's not R0 we did not take to be finite for all these situations. So if you take an R0, all of these things might change. For example, in the R out you might find that this is actually RP parallel R0 and all of that. But anyway, in general, at least the trend will be the same. Okay. So what were the problems with this op amp? So these were your approximations. But be careful, not consistent with all of the above results. Okay. So we took them for our own convenience. We took whatever combination was good. Okay. Anyway, if it's in an exam, I'll tell you what to take. So don't worry about it. Okay. And what were the problems of this particular op amp? What are the problems? First problem was finite gain. Second problem was R out is high. Okay. So we want to rectify these two things. When we go to the next kind of op amp. But before that, we should do one thing which we haven't done so far, and I thought I can avoid it, but I think we need to do it. Okay. So we need to find out the swing limits of this guy. So you can calculate the output and the input swing limits. I am not going to use the output swing limits, so I am not going to do that right now. I will only do the output swing limits, because that we need when we go to the next, when we go to the two-stage op amp. So we will only look at the output swing limits for now. Maybe in a more advanced course, you will do all the swing limits. Okay. Because the motivation of this course is not so much to help you design the op amp, it is only to understand what are the blocks inside the op amp and what are the implications of those blocks. We will look at the implications of these blocks in Monday's class. Okay. That is very important, because if you use the op amp, you need to know what kind of compensation there exists in the op amp. For example, the same 741 op amp which many of you would have used actually comes in two flavors. One is a flavor where it is compensated, another is a flavor where it is not compensated. Whenever you have compensation, there is a trade-off. It gives you stability, but there is a trade-off, and the trade-off is in terms of its bandwidth. So if you are careful, you can actually use the same basic op amp, but you can do the compensation on your own, so that you actually get better performance than the readily available compensated op amp, and that is something that I want to convey to you in the next class. So in order to get that, we need to actually understand the various building blocks, and that is the motivation for what I am doing now. Design of this, exactly how do you bias all these transistors, what should be the W by L ratio and all of that, that you will do if you take the next course on CMOS analog and digital ICs. The professor there will go through all of that in detail. Okay. So what I am interested in here is the output swing limit. And why do you think I need the output swing limit, and I am not so much worried about the input swing limit right now? Because I am going to connect another stage to this. So I should be careful as to what kind of stage I can connect. So for that, I need to know what is the output swing limit. Okay. So the output is measured where? Output is measured here. All right. And what is the input? The total input on this terminal, it is your Vg0 plus small Vcm plus Vd by 2. This guy is Vg0 plus small Vcm minus Vd by 2. Okay. Now let me call this full thing as V5, and let me call that as V5. Okay, let me just call it V5. All right. Now look at transistor M4. How have we biased all of this? This is I0 flowing here. So this current is I0, the bias value, right? So I should say this is bias I0. Okay. Because the moment I put this Vd by 2 and small Vcm and all of this I0 will remain, but the currents in these two arms will change. Okay. All right. Now the current here, quiescent current is going to be I0 by 2. Similarly, the quiescent current here is going to be I0 by 2, and then you will have the small signal current, which I am not going to write here, but that there will be some small signal current which will add to this, and there will be some small signal current which subtracts from that, and that is what is going to give you the gain. That is what we have done so far. All right. Okay. Now if there is a current of I0 by 2 flowing through this transistor M3, can you tell me something about its VGS? So I want to find out what is VGS3. when a current of I0 by 2 flows through the transistor. What is this? How do you get this? You can just say that I0 by 2 is nothing but the constant K3 corresponding to this transistor into VSG3 minus VT. This is a PMOS transistor, VTP whole squared divided by 2. Okay. So, this quantity is not VGS3, I want VSG3. So, what will this thing be? It will be under root of I naught by K3 plus VTP. Okay. So, if this is my VSG3, what about this quantity? What about VSG4? What about VSG4? VSG4 will also be the same, right? This is approximately equal to VSG4 when I naught by 2 flows in that circuit. Okay. Another way of looking at this is that because this amplifier, though we have said it has moderate gain, the gain is actually quite high, right? The gain is about 100. It's not small, which means that your VD can actually be very small and still you will get a V5 which is quite large. Correct. So, in the analysis you can actually forget about your VD. When you are looking at the swing limit, you can assume that over here you can forget about this quantity. Okay. And VCM is also going to be very small compared to VG0. So, pretty much you are only worried about this VG0. Okay. That is enough to crudely get an estimate of what the swing limits are. Okay. We are doing this very crudely. It's not very important as if to do it in a more rigorous fashion. Okay. All right. Now, tell me if V5 goes up, what do you think will happen? If V5 goes up, what do you think will happen to M4? No, I want you to tell me whether it will go into, does it have a tendency to go into saturation, triode, cutoff? Assume initially it is in saturation. Now I am increasing my V5, which means what am I doing? I am decreasing my VSD, right? Implies my VSD for this transistor 4 is going down. So, what do you think will happen? It will go into triode. Which one? V5. This is 5. V5. That is VSD. Correct. Oh, okay. Sorry. VD. Okay. Sorry. Yeah. Good. Which means this VSD actually increases or decreases? VSD, be careful. No, what I said initially is correct. Your VSD actually decreases because this is source, this is drain. Source is fixed at VDD. You are pumping up only your drain. So, what will happen to this difference of VSD? That will fall. So, what I wrote was correct. So, this thing has a tendency to go into triode. Okay. So, how do you avoid it from going into triode? No. I just want to know what is the maximum value of V5 you can have in terms of this VSG and all of this. What should it be? So, can you show that this V5 must be less than VDD minus under root of I0 by K3, right? How is that evident? So, how did you get this? Because saturation implies VSD must be greater than what? VSG minus VT. which implies that V, this is, what is this? This is Vs minus Vd greater than Vs minus Vg minus Vt. So I can cancel my Vs from both sides, and then I can take my Vg on the other side. So Vg must be greater than Vd minus Vt, and essentially that is this, right? Is it that? But where did your Vg come from, all of this? So this is not the right way of looking at this. Actually, you take it from this. Okay, yeah, don't look at it this way. This is a more painful way of doing it. Because you know a current of I0 by 2 is flowing, right? Which means that my VSG is nothing but this quantity, right? This quantity is, this is VSG minus VTP. This quantity is nothing but root of I0 by K3 plus VTP minus VTP. So that goes, and VSD is nothing but V5 minus VDD. Sorry, see, it's late in the afternoon and it's hot, so that, okay, VDD. Good, all of you are awake. All right, so this gives you what I wanted there. Okay, then what is the next thing that we can do? So we took the case when V5 goes high. What happens when you keep reducing V5? What do you think will happen if I reduce V5? What will happen to M2? M2's drain will fall. So M2 can go into triode, right? If M2 falls too much, sorry, V5 falls too much, M2 can get into triode. So how do you avoid this? What do you have to ensure? VGS of M2 must be greater than VDS of M2 must be greater than VGS of M2 minus VTN, and a current of what is flowing? ID by 2 is flowing. So can you tell me what this is? Okay, here we can do what we said. What this is identical to saying VD of 2 must be greater than VG of 2 minus VTN. And then I just mentioned that in this thing VCM and VD by 2 will usually be small quantities. So it's essentially going to be this VG0 minus VTN, and VD2 is essentially your V5. Okay. So what's your complete condition? V5 must be greater than VG0 minus VTN and must be less than, what was the previous condition? VDD minus square root of I0 by K3. Okay. Now all of this really does not make much sense unless you see it pictorially. So to show it pictorially, and that this is what we need actually for proceeding, let me say that this quantity is my VDD, this is 0. Where is this limit going to come and where is this limit going to come? First let's take the higher limit. Where is this limit going to appear? Somewhere less than that. Okay, this is going to be this limit, and where is this limit going to appear? Somewhere greater than 0. Alright, and it's going to depend on the value of this VG0, right? So you have to choose your VG0 carefully such that all your transistors are biased and all of that. As I mentioned, I am not going to tell you how to do that, people do it. Okay, don't worry about that, assume that everything is biased well. So which region can you operate in? So, you should avoid this region and you should avoid that region, and you are allowed. So, V phi can basically swing in that region. So, the take home from all of this is the swing of V phi is the upper bound on the swing on V phi is less than VDD, the lower bound is more than more than 0. So, if you take for example an op amp like what you are using, which operates out of two supplies, plus VCC and minus VCC, right, plus 15 and minus 15, then your output can go all the way up, almost close to 15. The input can go all the way above minus 15. So, one simple way of doing everything, one simple way of biasing is to assume VG0 is 0. Okay, that is the typical mode in which all your op amps work. If you assume VG0 is 0 and you have the upper power supply to go to plus 15 and the lower power supply to go to minus 15, things will usually work well, and that is what your commodity op amps, that is how they function. Okay, all right. So, now let us just take this particular thing and move forward, but before that, what do I need? I need to draw my op amp again. So, all of you please go and draw it again. I am now going to cascade this with something else. This is easy to draw. In fact, this is one of the most beautiful things that you can draw in this particular course. And what comes here? I am doing this because I am not going to connect, I am not going to show the other current source. So, this arrow means the other current source. Okay, all right. Now, which is the plus terminal of your op amp? That is, the question I am asking is, this whole thing is a single stage op amp. So, there is a plus terminal, negative terminal. So, which is your plus terminal? This is your plus terminal. Which is the negative terminal? That terminal. Okay, because you want how do you determine which is plus and which is minus? If I call this as V1 and V2, you want this output to be A times V1 minus V2. So, that is the way, if you configure it this way, you will get this, otherwise you will get minus of that which you do not want. All right. Okay. Now, what were we looking at? I am trying to make a two stage op amp. So, what should I do for a two stage op amp? I should take this output and then I should cascade it. Now, what do you think I should cascade it with? What other amplifiers do you know? Which is the only amplifier that gives you gain? Common source amplifier. So, how many common source amplifiers can you make? Basically, two. You can either make it with an NMOS transistor or you can make it with a PMOS transistor. So, the reason why we did the swing limits and all of that is to tell you which one you should choose, which one is more convenient to choose. Okay. So, I am going to draw an NMOS and then a PMOS, and then we will discuss based on what we had for the swing limit as to which one is easier to have. Okay. If I were to have a PMOS guy, how will it look? The PMOS common source amplifier will have that there, input here, right, and then actually I do not want to have that there, I want to have it slightly lower so I can connect everything easily. Okay. And then what will be there at the bottom? Some kind of current source. I call this some current source I2. Okay. And what about for an NMOS amplifier? Just the reverse of that, right? So, the I2 will be up there and then all right. Now, which do you think is preferable to use? Which do you think is preferable to use? For that, we should go back to this one, right, and take our swing limits. Okay, those are our swing limits. Now, draw the swing limits here. You had something here like that, okay, and then I am going to very suggestively draw the other one. as being there. Okay, because you see what's happening, your upper limit is a function of this Vg0. So depending on what Vg0 I choose, I can have this here. So for example, I can have a situation where all of this region is forbidden. Okay, this is your lower limit, I'll call that VL. This is your upper limit, I'll call that VH. So this is my VL and this is my VH. And VH you can, it's VDD minus something, so you can expect it to be close to the power supply rail. Okay, now which do you think is easier to use? The PMOS or the NMOS? Really? The way I have drawn it. So for this transistor, if I2 is flowing, what do you expect this guy to be? Bias value. What do you expect that to be biased at? Again, simple. You have I2 flowing. I want you to tell me what is VGS. What is that going to be? It will be VDD minus, or I just want only VG, not VGS. It will be VDD minus VTP minus under root of 2 I2 divided by K5. You see how you get this? If you have I2 flowing through this, you calculate what your VGS is. From that you calculate what VG is. And what should this be? For this guy, what will that be? It will be VTN plus root of 2 I2 divided by K5. Why is it 5? Because I am calling this transistor M5, I am calling this transistor also M5. Oops, in the previous thing I called which one M5? Okay, let me not call that M5. Let me call this as, I'll call this as MB and MA. Okay, just for fun. You can call it anything, just something. Anyway, there's no phi in this one, right? So there's no problem. Okay, all right. Now, based on this, can you change your answer? Look at this guy, what you require, right? This falls in this gap very easily. This one, it may not, right? Because depending on what value of this gate voltage you choose, you can have this guy fall somewhere in this region. Okay, so usually this is the chosen one. Alright, go think about this, it's very straightforward. Okay, the way I have drawn it, it may confuse you, but usually it's the PMOS stage which is chosen. Or in some op amps, what you will see is that the differential amplifier will be a PMOS differential amplifier, and then the common source second stage will be an NMOS second stage. So you will see this thing of one being a PMOS stage, other being an NMOS stage. Again, the motivation here is not to ask you to design it, it is just to understand what is commonly available. The reasons for why and all of that you will see again later. Okay, all right. Now, if I have chosen the PMOS one, how do you think the circuit should look? Again, draw the whole thing. Okay, because I like to draw this. No, as you draw it more and more times, it goes into your head. If you don't draw it and look at your phone, then nothing will go into your head. Okay, how did this look? I am drawing it so that all of you can also draw it. If I keep copying and pasting, then you guys can't draw. Okay, now how do I draw the next stage? I want to only use one current source. And then what should I do? So input, I am taking the output from here and I am connecting it to the input there. Alright, that is my stage 1 to stage 2 connection. This stage 2 needs a current source, right? How do I get that current source? From this same current source, I can just alright. Everything good? Okay. Now, do you realize something that I have done which we did not do when we were looking just at the common source amplifier? Do you see any capacitors? Why? No, those are the internal capacitors I am not talking about. There are no coupling capacitors, right? I am taking an input signal, I am just, I am taking this output from this guy, correct? This is VO1 and I am directly coupling it to the next stage. How come I have got rid of the coupling capacitors, and why do you think I have got rid of the coupling capacitors? DC component gets cancelled, that is one point. Another point, you notice that all the op amp is finally going to operate in feedback. So for example, I will have a thing like this, right, where this is my input, so I call that Vi. The simplest possible op amp configuration is source follower, right? What is the output here? Vi. Alright. Now this Vi, if I give 1 volt, I should get 1 volt. If I give 2 volts, I should get 2 volts, right? So this works for both AC and DC. I want my op amp to work for AC and DC. If I put coupling capacitors inside my op amp, coupling one stage to another stage, what will happen? It will no longer work for DC. Because I want the operational amplifier to be a very general purpose amplifier, I want my operational amplifier to work for AC and DC. It's a very, very important point, right? And DC signals implies avoid coupling capacitors in between stages, and that is the reason why we chose the PMOS amplifier, because we have to match the operating point of this such that for that particular operating point the next stage also is biased in saturation. So what we will do is somehow we will choose this value of VG0, and I just mentioned, I gave you a hint, if I am working with a dual supply op amp, then if I choose my VG0 to be 0, everything will work usually, right? It's a good choice. So then I don't need to do anything. So if I choose that like that, I should ensure that whatever the output I get from the first stage op amp, that output will have some bias value and there will be some deviation above that bias value. That bias value should be such that it biases the subsequent stage in the correct such that all the transistors are in saturation. Okay, so that's why you don't want to have any coupling capacitors anywhere. You choose things in an intelligent manner. Okay, now this is your amplifier. Now I want you to calculate what's the gain of this amplifier. Can you do that? So I'll name my transistors M1, M2, M3, M4, then M5, M6, then what else did I have? Okay, this one I will not worry about. I will call this as M0. I will forget about this transistor. Okay, pardon me, I am using different nomenclature for different pages. Alright, now I am going to be smart with my guesses, but I will try and be consistent with my approximations. Okay, so the approximations for various transistors. You remember what was the gain of the first stage? It was GMN into RP. So basically the gain part of it came from the NMOS but the load came from the active load which was given by the PMOS device. So what I will do is, wherever the active load is there, I will include the resistance for that, but whichever transistor is giving me only the GM, I will not include any resistor for that, okay, just to be consistent. It really does not matter, but just to be consistent. So if I were to follow that idea, what can you tell me? What about M1 and M2? Okay, these are my approximations. What about M1 and M2? They have a gain which is, say I will call them GM1, GM2, but then its resistance will be, this will be the Rn, I will call that resistance infinite. Okay. What about M3 and M4? Let this gain be GM3 and GM4, okay, but let it have some Rp. What about M0 and what about M6? M0, it had GM0, and what should I do about its gain? Let me assume that its R0 is infinite, okay. And M6, realize that M6 is the active load for M5, right? So I am going to have this as GM6, and then what is its load? So I will not keep that as infinite, I will keep it as R6. So basically, if you look at this, what are the non-infinite values of resistors? This one and that one, okay. So I can call this actually, because I am working with a slightly different thing, instead of Rp, I will just call this as R3, okay. So you have these two resistors. Now how do you think the incremental circuit of this will look? Who wants to guess, draw this with all the transistors and all the incremental sources? Okay. So this, we are using it as both actually, right? It also ensures that that current flows in, right? And when M5 looks at what's the kind of load M6 is providing, it is actually providing an active load. Similar to this kind of thing, right? You don't want to have too many different things. So this guy is this is the differential amplifier. Why? Because M6 is actually the active load for M5. See, if you did not have M6, you would have put a resistor, right? But the resistor will not give you as high a load as you would want. So you, in the spirit of what we have been doing, let's have an active load. So this is a differential stage. With active load. This is a PMOS common source amplifier, again with an NMOS active load. All right, is everyone with me over here? Okay. Now let's do this smartly. Let's not trouble ourselves. This is the positive terminal, that's the negative terminal. Okay. Now we can do it actually in a smart way. We remember we did the Thevenin equivalent or the Norton equivalent. Let's go with the Norton equivalent. So if I were to go with the Norton equivalent of the first stage, what is here? Plus minus Vd. And what was the stage? It's a Norton equivalent, so it should have a current source. Should the current source point up or down? And what is the load that it's driving? Rp. And what is Rp here? Go back, Rp, we changed the nomenclature. It became R3. And this one, what is the gain of this one? GM. What is the value? GM 1, 2, 3, what is it? GM 1. And what is the value of the voltage? Vd. Okay, only thing I have to fix is the direction. Is it going up or down? Up. Why is it going up? Because this is a non-inverting stage, right? It gives you A times Vd. So if this is there, it will give you A times Vd. Okay, very good. What about this terminal? Is it shorted to source or is it floating? Careful. This is a single-ended output, right? That is to source. Sorry, to ground. Okay. What happens to the second stage? Second stage is a straightforward common source amplifier. Common source amplifier has one rail connected to ground. What about its output? It has a current source. And what is the load? I am only giving the active load. So what's the value of the resistance? R6. Okay. And this arrow, does it go up or down? Why is it going down? Because it's a common source amplifier. Okay. So that is my drain and that source. All right. And that's my output. So what happens because of that connection of first stage to second stage? This is connected here. So this is my VO1 and this is my VO2. This is my incremental circuit for differential signals. Why are we only worried about the differential signals? Because we know that the common mode rejection ratio is actually quite high. So we can forget about the common mode incremental signal to only are worried about the differential mode incremental signal. All right. Okay. Now can you tell me what the gain is? Quickly. It's equal to this what is this value of GM? GM5 times VO1. Is it 5? Yes. It's 5, right? Is this transistor which is giving you the gain? In the differential pair, M1 and M2 were giving you the gain. Both of them had the same GM. In the common source amplifier, M5 is giving you the gain, M6 is the load. Okay. So it's GM1 into GM5 into R3 into R6 with a minus sign. Okay. Now is that minus sign good or bad? First, is this gain high or low? High, right? Why is it high? Because so if you look here, this typically will be order of say 100 microsiemens, GM5 another 100 microsiemens, right? What about microsiemens? Siemens S is capital, sorry. What about R3? That is it's the resistance provided by the active load, so it will be high. So you can assume this to be about 1 mega ohm. What about R6? Again 1 mega ohm. So all of this will become approximately minus 10 power 4, which is infinite, right? Which is high. It's better than a single stage amplifier. Okay. And what else do you want? Output impedance and all will come to. First, does this look like your amplifier? Does this look like your op amp? I mentioned that when I have an op amp like this and I have V1 here and V2 here, I want my output to be some AD times V1 minus V2. But this is giving you what? V2 minus V1. So what can you do? What should you do? Huh? No, I don't want to put another stage. Tell me if you can do it with what I have. Go back. Who told you that this is plus and this is minus? Right? You can always flip it, right? So you flip it. So I can write this down as flip the positive and negative terminals of the differential stage. All right. So so the reason here is I want a positive gain, but the circuit as developed gives negative gain, and so you flip the positive and the negative terminals, you will be okay. All right. So should I draw the circuit again? But I want to. Okay, just so that everything is consistent. It also becomes a matter of record, right? So I don't. Okay. All right. Now what should I do? Flip this, flip that. So this becomes my negative. This becomes my positive. Okay. And I take my output here. All right. Now what happens to my this incremental picture that I had drawn? How does that change? Does it change or not? Can you tell me what the change in this guy will be? Okay, we have drawn it also such that. All right. Okay. So what do you think will be the change now? Huh? No, VD I want to retain like this. I want to have plus minus, and this is going to be grounded. So what should I flip? Which current source? First or second? Why second? I changed the plus and minus to the first one. How can you go and change the second one? Yeah, it has to be consistent, right? Because if I flip this direction, it means that the output to input of this stage has got flipped, which has not happened. The output to input of this stage has got flipped. So which one should I flip? First one. Should go, so this should go down. So now what will happen? V0 will be a negative quantity times Vd, V02 will be a negative quantity times V01. So completely you will get positive gain. And what will the gain be for this? Your differential gain will be, what will it be? Plus GM1, GM5, R3, R6. All right. Is this good? This is good. But does anyone smell a rat? There's a big rat. What are you doing here? You're coupling two amplifiers. What did we do when we spent a lot of time looking at coupled at cascaded amplifiers? Right. So far I have not drawn any capacitor here, right? I should draw a capacitor. And what will happen to that capacitor? I can actually have lots and lots of capacitors, but I will not trouble all of you and not trouble myself. Okay. So now I'll introduce the capacitors and then talk about what the problem is, and then the solution to the problem possibly you can think about, or we'll give it as a tutorial question or as a guided question in the exam. Okay. So in your quiz you looked at one kind of compensation. What was that compensation? No, dominant pole compensation. What did I do there? I added another block which had a pole at an extremely low value of frequency, so that one dominated the entire response, and so that at the unity gain cutoff frequency, at the unity loop gain frequency, you got a good enough phase margin. That was what we did in the quiz. Okay. If we want to do the same thing here, we have to cascade another stage. We don't want to do that. Using these two stages, can we do something? All right. So in order to do that, I want to introduce the capacitances. Where do you think I should introduce the capacitances? Okay, it can remain, you will have capacitances at various nodes, but to just convey the essence of the problem, what I will do is, I will say that there is one capacitance sitting here, I will call this as CL, and I will say that there is one capacitance sitting here, I will call that as C1. These are two parasitic capacitors. You remember we discussed all kinds of parasitic capacitors. I am not going to put all of those. I will just introduce two parasitic capacitors, C1 and C2. Okay. So, I have introduced two parasitic caps C1 and CL. Okay, where will those capacitors appear here? Where will C1 appear? And this will appear here. Okay. Now, what do you think will be the response of this guy? What will be the response of this guy? How do you calculate it? There is an R3 parallel C1, there is a source here. So, what will V02 by Vd be? Will be what? Minus GM1 into R3 into 1 by 1 plus J omega by omega 1, and what do you think omega 1 will be? 1 by R3 C1. Does this look reasonable? Because at omega equal to 0 you get back your original result. Okay. Then what is, no, this is not correct. This is V0 1. What about V02 by V01? This will be minus GM 5 into R6 into 1 by 1 plus J omega by omega what? 2. And what is omega 2? 1 by R6 CL. Okay. Now, how do you think the frequency response of the complete system will look? So, your V02 by Vd will be GM1, GM5, R3, R6 into 1 by 1 plus J omega by omega 1 into 1 by 1 plus J omega by omega 2. Okay. And I can call all of this guy as some DC gain A0, and so this essentially becomes what we had earlier, right? We will finish in about 5 minutes. We had V0 by Vd as some DC gain divided by 1 plus J omega by omega 1 into 1 plus J omega by omega 2. Okay. What is the frequency response of this? How will this look? So, I should first put my omega 1 and omega 2 here. Okay. And now, let me assume that say this is my, say omega 1 is here and say omega 2 is there. Then what will happen? Up to omega 1 it's going to be like this, then it's going to fall at minus 20 dB per decade, then it's going to fall at minus 40 per decade. Very good. All of you have at least got this one aspect of what we have been doing over and over and over again. Right? Good. Don't ever forget this. Okay. Now, how do you think the frequency, the phase response will appear? It will start at 0. Then, what is the final value? Minus 180 degrees. Okay. This will be minus 90 degrees. Minus 45, minus 135, 135 is not drawn correctly. Okay, and then what at this point it will be minus 45, then it will become minus 90, minus 135, and then as at a very high frequency okay. Now where is your unity loop gain frequency in all of this? I have not told you where it is, right? And also I have not told you what kind of feedback loop this particular thing is operating in, right? So assume that this particular op amp actually is connected, say, in some very straightforward connection. What's the simplest connection that you can think of? Plus minus, and then I don't have any feedback component. I just put this here, and then I have that load capacitor, right? So that load capacitor is sitting here. This is my V in. Okay, sorry, this is not V naught by Vd. This is V naught by Vi. Okay, so in this case, what is your loop gain? I call this as some A of S. What is loop gain? Loop gain is still A of S only, because your feedback path has a gain of 1. Okay, that's just a simplification. Now I have not really told you this quantity is A0. I have not told you where the 1 is. So 1 can be anywhere, correct? And that depends on what is the value of A0 and all of that. Okay. Now in order to compensate things, what is it that you want to achieve? Why do you want to do the compensation? But this is a second order system. What do you know about a second order system? Always stable. So what is it that you want to do? It's a second order system, so it's always stable. If my input goes like this, what about the output? What can you expect at the output? It's a source follower, right? So output will become input, but how will it? What's the only difference? This system is always stable because this is a second order system. But you can have a damping factor zeta, correct, which might be less than 1. If it is less than 1, implies what will happen? You will have ringing. So for that less than 1, you will have something like this, correct. If the number is even lesser than 1, what will happen? It will keep on ringing and never die out. Okay, so this is, say, zeta is equal to, say, 0.9, and say okay, that should be in red, and say this is zeta equal to, say, 0.01. Okay, so you essentially want your zeta to be, what do you want zeta to be? 1. And what does that imply? Implies what is the phase margin? You want to get 76 degrees. So what can you do? You have this circuit here, right? Something has happened. Now you want to do something to change this. It's 2 minutes. Okay. So I can introduce another capacitor here, right? I'll call that some C alpha. If I given a high enough C alpha, what will happen? The pole corresponding to C1 and R3 will go to the left, and that will help you stabilize things. Okay. Now I don't want to put a capacitor here. If I have to put a capacitor here, I have to put a really large capacitor. What can I do to avoid that? I can use the Miller effect. Where should I put the Miller effect?
After the stage 1.
If I put my capacitor here, okay, then what will be the effective C alpha that this C is, I'll CC into 1 plus gain of the second stage, which will be what? 1 plus, what's the gain of the second stage? GM 5 R6. The gain is actually minus or rather in this particular case minus A2 is minus GM5 R6, right? The gain is negative. No. In this expression of 1 plus A2 you should use, you should use only the magnitude. Okay. So you will have this CC put over here. Okay. Now in the next class we'll discuss how to design the CC, but if I just go back here, where do you think that compensation capacitor will sit? In this particular circuit, where do you think the compensation capacitor will sit? So these two capacitors C1 and CL are parasitic, right? So I'll remove those. I don't want them now. They've done its job. They exist, but I don't care. In order to compensate everything, I'm going to introduce one value of capacitor. Where should that go? It should go between output and gate. So you will see a capacitor in all of your circuits going between this terminal, right, and the gate. Which gate? Okay, so go back and see where that should appear, because if you connect it like that, it will get shorted. Okay, let's go back and look at it systematically. This is drain of M5. So drain of M5 is here. Then this is gate of here, right? So where should it appear? That will be a compensating capacitor. Okay. So if you go and look at any op amp, this is your 2-stage op amp. Just go and look, for example, at the 741, or many of you are working with various op amps, right? Go and look at its data sheet. You will see this essential stuff sitting inside. They might have made it with BJTs, they might have flipped it, they might have used the PMOS first stage and then an NMOS second stage and all of that. But in essence, you will see this, and you will see this compensation capacitor sitting inside. How do you choose this compensation capacitor? We'll look at it in the next class, and that will really teach you as to why we have done all of this nonsense, right? The main important thing is, when you use an op amp, you should be aware of certain things, right? And those things are very important when you actually design a circuit. And to understand why the op amp behaves in that way, you need to understand the internals, and that's why we have gone through all of this. Okay. All right. Thank you very much for patiently listening. We'll meet next week. Thanks.